we're going to pick up this problem again. Now, what I want to do today, I've explained to you about the work for Thursday. Today, I want to get through section 2.5. If by chance things go like they did in the other section, the 8 o'clock class, I didn't get quite through 2.5, we're not going to worry about it. So we're going to get through as much as we can of this stuff, and then I want to hand back your quizzes. And we're going to talk about your quizzes. This is the first quiz of the semester, and it's always an interesting experience for everyone to have that first assessment. So we're out of here at 12:15. I want to give myself at least 15 minutes to talk to you about that. So we'll try to make sure that if I don't seem to see the clock and it's getting close to noon, let me know, and we'll cut it off. Okay. We're talking about, in section 2.4, continuity. So to get us started on this, let's do a little review. Continuity review. What I'm going to be asking you is, what are the 3 criteria for continuity? Okay. 3 criteria. So think about that. Okay. Whoops. Hang on a second. I want to make sure we see the time here. Okay. 3 criteria. What's the first one? Evelyn, give me one. So f of x is defined where? At where? Yeah. At a point, an input value, x equals c. So let's see. Let's see if I can do better than that. So here is c. Okay? If I go up here, visually we've got a good idea of what continuity is. Visually, is that function continuous? Oh, it is. As it's drawn, I got my seating chart here. As it's drawn, Matt, what do you think? Oops, am I on the wrong person? Matt? With the, you are? You're Scott. Well, Scott, you're sitting where April sits, I guess. Where do you usually sit? Okay. Oh, I'm sorry, my eyes got on the wrong one. Okay. Okay, well, we'll start over again. Scott. No, okay. Why is that function not continuous? Yeah, the open. Well, what if I do this? Is it now defined? Okay, it is defined, but we know, we can see it's not. So our eye is going to tell us if we can see it whether or not it's continuous, but we have to have these 3 conditions for the case when it's not obvious visually. Okay, so is the function defined at x equals c? And our answer to this would be yes. Okay, number 2, what's our second criteria? Because at this point, if this is the only thing I've got, I'd have to say it's continuous here. We know it's not. So what's our second criteria? Yes?
The limit of f of x
at c? When x equals c? How do we write limits? The limit as what? Yeah, as x approaches c, from what direction? Jessica, from what direction on a limit? Yeah, from both sides. So as we approach c from this less than the c value and the greater than c value, does the limit exist? So, take a look at that. Does the limit exist? Ooh, I saw a shake of the head. Shake of the head. Peter, did you shake your head? Oh, okay. Well, it's like an auctioneer, you know. If you nod a little bit, I think you're bidding on something. So, tell me, does the limit exist as x approaches c? There's a question in that yes you gave me. I'm sorry, what was that?
I just woke up. I'm wrong too.
Oh, you know what? I got a suggestion for you. Get up at 5:30. Okay? I'll bet you'll be awake now. Okay, we'll pass you on this one. Let's see. Beside Peter's, Eric. Eric, does that limit exist?
Yes.
How do you know?
Because
Okay. Okay. If I come up from this direction, I approach here, and I come from this direction, I approach to here, and yeah, you could clap. So the limit exists. Now, according to the first two criteria, then this function must be continuous at C. But the third criteria, the third condition, is the most important one then. What's our third condition? Say it again, Danielle. F of x equals f of c. That's what this says. Or the function, I can't really say f of x equals f of c. What's our third condition? Try Scott again. X? What? F of c. So what does this mean to you? The limit of the function is up here, right? We'll call that b. The function's value is how much? A. Is the value of the limit equal to the function's value? And the answer is no in this case. Okay, so this is not continuous then at C. Is it ever continuous at any point? Yes. We're just looking at the value C at this point. Okay, be sure you know that three conditions for continuity. Evelyn.
If we say the exact same, we need to prove it by saying
If I ask you to discuss the continuity using the three conditions, yes. Okay? If I don't ask you to be, if I'm not that specific with it, I'd have to take your answer for whatever I asked you. Okay. So we ended last Thursday with this problem. We need to continue with this problem now and see what we can determine on here. Find the constant A, and again, I talked to you, I know, about A. That's a letter A, that's a variable A, that's not a article of language, you know. Find the constant, the value for A, such that the function is continuous on the real line. Now, we also talked last Thursday about what we knew about the graph of this function. For instance, on this is a piecewise defined function. It's defined in pieces. So the second piece of this function, if this is the value A, the second piece of this function tells me that the function is what at? It's just a point, isn't it? Some of you know last week were trying to tell me it was a line. It says when it equals A, the output value is 8. We'll put 8 up here. And so all I have from that second piece is that. That's it. It doesn't say that it's equaling A for a variety of inputs. It says one input. Okay, this is the piece then that we need to work with. So I'm going to bring this piece down because right now limits are this problem, this function is you can kind of think of it in the same vein as we do our limits. I need to know x does not equal A, but what if I put A in here? What would happen? Yeah, zero denominator, it's undefined. I can't do that. So let's bring this down and let's look at this. Is there another way that we can write this piece of the function so that we do this to say that we're going to remove a discontinuity? It's really not going to be removed, but we can at least rewrite the function so that we end up with something that is equivalent except at a point. Now you got a hand up, Peter, right? Okay, good. Okay. Okay, and I can do this, and I love being able to do that because, continue.
Cancel out.
Okay, so this piece is equivalent to x plus a. Now, I don't know what a is. I got to find that. That's what the problem's asking. What value would a have to be? But I can tell you something about the graph of this piece. It's going to be a what? Yeah, it's a linear function at this point. It's going to be a straight line. So I don't know for sure what that's going to look like, but I can do, whoops, let's see if I can do better than that. I can draw a line that goes here. It's going to have an open circle and then continue on. That's what the first piece is. Because I always have to go back to the original, and I know in the original I can't use a, but it is equivalent to this line. Now, how does this, though, help me out? I've got the open circle from the first piece. I get down to here, though, and then that becomes the point. And I can, it's a pretty big point, but I can fill in that point now. Now is the function continuous? Absolutely. Absolutely. Now, the question is, what is a? What is the value of a that makes that true? Now, I have to tell you a little secret. When I look around and I see someone nodding, it's just the little imp inside of me. I just want to call on that person so badly. So I won't, if I do that, I won't do it to be embarrassing you, but it's just I can't help myself. So just kind of be careful. If I see you nodding, I'm going to, and if I call on someone, it doesn't mean that they were nodding, okay? So don't make that assumption. Okay, so here we go. I want to know what A is. That's the whole purpose of this problem. I get the picture now. I know what I'm going for. Okay, let's look at this. When we look at this problem, the fact that I can fill in the empty hole with the value a, 8, or with the a value, this point gets filled in, tells me something about the output of this function, this piece, and the output of this piece. What's it tell me? The fact that I can fill that in. Remember, it was an open hole before, right? And all of a sudden I could fill that in. It has to be 8. Yeah. This is an output value. This is an... Are you with me on this? Because some of you missed it on the quiz. This whole thing, this fraction, expresses an output value. The output of this function is going to be the same thing as the output of the second piece of the function. Well, we did a little bit of work, and we found out that x plus a equals 8. Same thing. The output of this function has the same value as the output of 8. Now, here's where you have to kind of be the mathematician. The mathematician doesn't always abide by all the rules. Did you know that? We say, well, suppose, just suppose, what if? What if x could equal a? Time? Thank you. I'm going to stop this in just a couple of seconds here, but suppose x could equal a. What would that tell you about this? So think about that while I stop this and save it.